Hey everyone. In this video, I'm going to talk about some key concepts in statistical inference. So, broadly, statistical inference is always about using the data that we have, that we observe, to learn something about the data we don't have, right? And that could be in the context of prediction, it could be in the context of causal inference, and so on. But it's always making an inference based on something we have about something that we don't have, that we can't observe, okay? And the key issue in inference is that we have to quantify the uncertainty based on some assumed probability model for the observed data. Okay, so in this video and in the book chapter in the chapters for this week, we cover a lot of kind of the basic tools in probability modeling and estimation that kind of help us both make those inferences and properly quantify this uncertainty. Okay, when I started introducing this idea of statistical inference last semester, I started with this simple visualization of kind of this producing data and sampling data from a population, engaging in exploratory analysis, and then based on some probability model, making inferences about the population. And one thing to that I want to kind of emphasize is that in the first semester we kind of focused most on one key aspect that is a source of uncertainty, which is sampling uncertainty, right? We wanted to quantify how much variation there will be across repeated samples, right? But that's ultimately only one factor that influences our uncertainty around our inferences and around our estimates, right? So in general, given that statistical inference is used to learn from incomplete or imperfect data, there are different kind of paradigms we can think about for the role of inference and the type of uncertainty we need to quantify, right? So these three kind of standard paradigms, the first one is the sampling model, and that's what we kind of focused on most and what is also visualized here is this uncertainty based on the fact that we cannot observe the entire population. We just take a sample from that population, depending on what kind of sample we take, whether it's a perfect random sample or some other stratified sample. We have to take into account that sampling procedure to quantify the uncertainty around our estimates for the inferences that we want to make about the entire population, right? So if we're trying to learn some characteristics of a population, for example, the mean and standard deviation of party identification in the United States, we have to estimate them from a sample or a subset of that of that population, and any deviation between the sample and the population, random deviation will introduce uncertainty. Okay, but the key is that this is not the only source of uncertainty in our inferences. There's also the issue of measurement error and the measurement error model, right? So, and the underlying idea here is that even if we had a even if we were able to observe the entire population, there's still uncertainty or there's still error when it comes to measuring our key concepts of interest, whether it's the dependent variable or the independent variable, okay? And so we have to take into account measurement error as well when we want to, correctly quantify the uncertainty around our estimates when we're making these inferences. And then the third aspect is ultimately imperfections of the models that we apply to the real data, right? That's kind of a third, it's related, but it's the third component, right? Our model specifications, the types of variables we include, or maybe the functional form, is not a perfect reflection of the actual underlying process, the underlying data generating process. So that can also introduce ultimately uncertainty around our inferences, right? So ultimately, what we have to do is we have to consider all three issues when constructing and working with a statistical model, because they all impact to what extent we can use our analysis based on our observed data to make inferences about what we don't know. Whether that's a population or whether that's a causal, the causal inference. There's always something that we cannot directly observe, and we're trying to make inferences about. Okay, and we have to take into account all three of these issues when we want to quantify our uncertainty. Okay. In that context, we talked about this idea of the sampling distribution, mostly from the perspective of frequentist statistics. In general, the sampling distribution describes the set of possible data sets that could have been observed if the data collection process had been redone, along with the probabilities of those specific values or realizations, right? And so what is important to keep in mind, despite the fact that we talk about the sampling distribution, taking into account these three different paradigms, this variation between different realizations of the data they're not only based on the sampling process itself, but they could also take into account different realizations in terms of measurement error and things like that, right? So the variation in this sampling distribution of possible data sets and possible analysis and possible results ultimately, the variation does not need to come from the sample process itself, right? So and that's why in the book it is mentioned that maybe a more accurate kind of description or label would be kind of a probabilistic data model rather than a sampling distribution. But we'll keep the term sampling distribution to kind of capture this idea, but now we keep in mind that this incorporates not only variation due to sampling, but also variation through other influences such as measurement error and so on. Okay. Lastly, the way we kind of think about this is that the sampling distribution itself, kind of the process of the sampling distribution in this broader sense, we can think of as a generative model in that it represents a random process which, if known, could generate a new data set, right? So that's a kind of a broader view of the sampling distribution as basically a random process that is never entirely known, but if it was known, we could basically recreate new data sets and new analysis again and again and again. So it basically represents the entire data generating process. Okay, therefore, ultimately, we think about this sampling distribution as a generative model that if we knew it, it's always, it's not observed, but if we were able to observe it, or if it was known, we could basically just generate new data sets for our analysis. Okay. All right. So in that context, we want to define a couple of key concepts that we mentioned before. Particularly estimates, standard errors, and confidence intervals. Okay, so in general, we use the data that we observe to ultimately construct estimates of parameters and other quantities of interest, right? That's what we do as part of our statistical inference, right? In this context, parameters are unknown numbers that determine some statistical model, right? So these could be coefficients in a linear regression, or like scale and variance parameters for the error term, and so on. So those are the parameters that can be used to potentially simulate new data. Okay. And then related to the parameters, we have different estimates or quantities of interest, right? And those are some summaries of parameters or data that we're interested in estimating from a substantive point of view, right? So this could be a single parameter, but it could also be like a function of multiple parameters or a combination of them. For example, when we think about predicted outcomes of a particular new data points as a potential quantity of interest. Okay. The standard error is then the estimated standard deviation of an estimate. And again, that's kind of the variation across, from a frequentist perspective, you could think of this as the variation across repeated realizations of the data generating process, so across sampling distributions. Okay. The standard error therefore kind of gives us a sense of uncertainty about our quantity of interest. And in general, the standard error is a function of the sample size. So it's this, as the sample size gets larger, the standard error becomes smaller, ultimately converging to 0. Okay. And we can, in the last semester, we learned a lot of tools, based on the central limit theorem to evaluate the statistical properties of estimates analytically, right? We kind of invoked the central limit theorem and derived formulas for the standard error for a mean or for a difference in means and so on, right? We can also do that, evaluate the statistical properties based on simulation, basically by simulating the whole data generating process or the sampling distribution, and then summarizing across kind of basically simulated outcomes. Okay, and we're going to talk about that technique and how to do that in more detail in the upcoming videos. Okay. Then related to the standard error, we can construct and compute confidence intervals, which basically specify the range of values of a parameter or quantity of interest that are roughly consistent with the data. Okay, we have to keep in mind that this is always kind of given the assumed sampling distribution. We talked, and in the following example, we'll talk a little bit more about how to kind of interpret these classic confidence intervals. For example, the 95 confidence interval, which basically describes an interval that over repeating sampling procedures should include the true value 95% of the time. And we'll use some simulations to kind of validate that for a specific example. Okay. Then when we do this, we construct these estimates or quantities of interest, we compute quantities of interest, we kind of specify the uncertainty based on sampling uncertainty and so on. One thing that is important is whenever we do this, we have to adjust our inferences to account for potential bias or unmodeled uncertainty. Okay. When we talk about bias, what we mean is that any unbiased estimate is correct on average, right? So over repeated data generating processes, the expectation of our estimate of our estimator should be equal to the true value. That's the definition of an estimator being unbiased, right? Another important thing to keep in mind is that our inferences for our estimates are conditional on a lot of assumptions. For example, ultimately the model being true, that we have unbiased measurements, that we have perfect random samples, and so on, right? But real data collection, actual data collection, is often imperfect. There are issues with measurement, and so on. And so wherever possible, we have to keep in mind that we include the possibility of model error in our inferences and in our predictions. Okay. So there are a couple of different, given that there are always potential sources for bias and additional sources of uncertainty, there's kind of this question of how we can account for these sources of error that are not, immediately included in our statistical model. Okay, and there are kind of a couple of strategies that we kind of should keep in mind in any kind of data or statistics exercise. The first one is to improve data collection. Data collection can be improved, for example, by using more careful measurements and sampling. So, for example, improving sampling frames or improving the measurements and surveys in order to get more precise and less biased results. Okay. We can also expand our models, right? So models can be expanded in various ways. For example, and we'll talk a lot about those, different model expansions in the regression context. For example, rather than assuming that a survey is driven comes from a perfect random sample, we could kind of incorporate differences in between certain demographics, or kind of assume that sampling is clustered in a certain way and things like that. Okay. The third strategy to kind of take into account bias and unmodeled uncertainty is ultimately, if we cannot incorporate it in our model, or if we cannot include our data collection, the least we can do is we can increase our stated uncertainty. So when everything else fails, when we cannot improve our data collection, when we cannot expand the model to incorporate specific structures in our data, we have to increase the uncertainty to account for these unmodeled sources of error. Okay. So for example, ultimately, if we're assuming that these errors are independent, we can just add additional variation to our uncertainty to give a more realistic account of how much uncertainty there is around our estimates. Okay. So in general, we have to be, as we kind of go through modeling and construct models and evaluate our model fit, we have to be aware of potential sources of error that are not in our models, and design data collections to minimize such errors. And in addition, set up suitably complex models to capture as much uncertainty and variation as possible. Okay. So one concern when performing data analysis and statistical inferences is the possibility of mistakenly coming to strong conclusions that ultimately don't replicate or reflect like real patterns in our data in the underlying population. Okay. Hypothesis testing and this idea of statistical significance is ultimately a way of to kind of quantify the possibility in the context of inference and decision making. So we're trying to ultimately quantify our uncertainty and minimize the probability that we're make wrong conclusions based on the data that we observe. Okay. And so now I'm going to give you a quick overview of hypothesis testing and statistical significance, as well as the critique. But looking at the time, I think I might take a break here and continue this in a separate video. So I'll break here, and I'll see you in a second.